Well, we're here today to honor our 2018 Alumni Merit Award recipient, Chris LaFleur. The University of Michigan College of Engineering Department Alumni Merit Awards are presented annually to accomplished Michigan engineers who exemplify inventive leadership, smart risk-taking, and broad impact. The award recognizes the alumni of distinction at the department level. And this year, our award winner is Chris LaFleur. Chris earned her doctorate degree of engineering degree in manufacturing engineering from us. Yay! In addition, she has a master's degree in fire protection from the University of Maryland, who will be playing in football this weekend, and a bachelor's degree in geology and mechanical engineering from the University of Rochester. She also served as a lieutenant in the U.S. Marine Corps, and we thank you for your service. Chris began her career as an environmental engineer at Parsons Engineering Science. Then she worked at General Motors, nearby us, managing corporate fire protection standards, and was responsible for property insurance and enterprise risk management. Currently, she is the program lead for hydrogen safety codes and standards at Sandia National Lab, responsible for the fire risk program at Sandia. Her main research involves evaluating fire risk for emerging energy technology. She's also served on the U.S. Department of Energy Hydrogen Safety Panel and has represented the country in developing hydrogen codes and standards for maritime applications. And her efforts has enabled the safe implementation of cleaner transportation fuels to reduce the U.S. reliance on fossil fuels and increase the availability of renewable energy solutions. So last year, she earned the Clean Energy Education and Empowerment for Women in Clean Energy Symposium Government Award. And this is a really great organization that works to counter the lack of representation of women in STEM fields. The goal is to basically close that gap and increase not only women participation, but leadership in these fields. And so Margaret noticed this. I guess, Chris, you took her ME 530 back in fall of 2001. Do you remember that? She can give you a quiz on it today? Sure, she can. And brought it to our attention. This is really important to recognize women for their leadership and high achievement in fields of clean energy. And I know that you've been very active in STEM and a good role model for all of us, and we really appreciate that. So I'd like to call up Chris and invite her to give a presentation on her work. And shall we give a round of applause for her for her work?
Thanks. I appreciate being here and appreciate the honor of this award. So they asked me to tell you a little bit about what I do, and I promised you fires, so I'm going to deliver those for sure. I'll have a little bit about my background, education, and work, and you heard a little bit, but I'll kind of go behind the scenes about the decisions I made along the way. And then I'm going to talk about two pieces of our research currently, and one is really exciting and cool, and the other one's really important. So I'll cover both of those. No, they're all important, but HEAF is where I'll start because that's, no, I'm not. I'm going to start with my background. Let's go backwards. So she said I went to school in Rochester. I had a Naval ROTC scholarship because I needed money to go to school, and I couldn't really decide what I wanted to major in, so I picked mechanical engineering and geology because I like rocks and I liked school and equations, and so what that shows you is that I was indecisive. But it turns out that those were two good things to have, those two qualifications, when I needed a job, because in environmental engineering consulting firm where I worked, I mean, they had geologists and they had engineers, and so I was able to wear both hats and do some site and soil remediation work. And I learned all about pollution and all the ways that all the fossil fuels that we get out of the earth go back into the earth and the water and the air. I was working at Parsons near the DC area for about 8 years, and my goal was to work for 5 years and decide what I wanted a master's in, since I was so indecisive. So I worked, and I found right around the Beltway this program in fire protection engineering, and I have to tell you that when I found out that you could study fire, that was like, boom, the penny dropped. I'm like, yes, 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 yes. And I also helped that I didn't need any prerequisites to start the master's program, so that was another thing. And I could drive around the Beltway. Before this program, I thought that fire was just things that happened to the forest and the houses and that were bad. And I didn't realize that you could do something about it, and you can engineer the fire out of the equation. And so in order to engineer the equation out to prevent a fire, you need to know how to make a really good one. So turns out, you may have noticed I'm a little bit of a pyromaniac. I like to set fire. I don't set fires. That's a rumor. So when I finished that program, I could basically go anywhere. And General Motors offered me a job because I needed a job. And I moved to Michigan and worked both here in Michigan, and also I took an international assignment, was the regional risk manager for Europe, Africa, and the Middle East, and that was fabulous. What happened while I was overseas is GM went bankrupt. Do you guys remember that? And that was not so fun. And so they told me, hey, guess what? You still have a job, but you'll be buying insurance and just renewing the insurance policy, and that's it. When you finish, then you start again. And I was like, oh, see that Ambassador Bridge? We're going to go over that because I'm not doing that. And I went back to my thesis at Maryland, where I had analyzed data, fire test data that came from Sandia National Laboratories. And my advisor there, I said when I was finishing, should I apply at Sandia? And he's like, no, they only hire PhDs. And I was like, oh. So that little comment that he doesn't recall making planted a seed in my brain that I might need a PhD. And so I was living here in Ann Arbor working for GM, and I found Arvin Atreya here, studies fire. And I was like, okay, it's in my backyard, and there's a fire guy there. I should come. But what I was doing for GM, or what I wanted to study for GM, was what was my dissertation ended up being about, was fires in manufacturing facilities. And so what was really cool about the manufacturing engineering program and the ISE department was it's totally custom. You can make it about important things that you want to study. And so I did that. And then I got my job at Sandia National Laboratories. Yep. I was moving back from Germany, and I sent out one resume, and I waited, and that was it. So this job is the bomb. The bomb. Literally, I don't work on the bomb, but the things that I do are the bomb. So I'm really happy, and I feel like everything I did up until this point I had to have done in order to do the job that I do. So I promised you fires, and now we're going to talk about some of the big fires. Just a second. I've been traveling. I need water. So we call them HEAFs. They're high energy arc faults. One of our customers is the Nuclear Regulatory Commission, and they have the regulatory power over nuclear power plants. And these are very important places that you don't want to have fires. And one of the things that we've been looking at is trying to quantify the consequence of a high energy arc fault. You can see in the italics the definition of a high energy arc fault. It's basically electrical equipment like switchgear, where there's either a fault from phase to phase or phase to ground, and it's caused by like loose connections or dust or a squirrel or like weird, anything can bridge this gap. And some of the electrical cabinets in a nuclear power plant are really high voltage, really high amperage, and you get a very energetic release. And it creates plasma, which is also conductive, and it's crazy. So when you do a risk analysis for a nuclear power plant, what you're looking at is what is the probability that you can't turn it off when you need to. Okay, so it's a core damage probability. It's probability of melting down your core. So there's certain cabling that goes through the power plant that you need to turn it off. And so every time, every compartment in the power plant is analyzed, and every type of scenario fault. And so when we look at a bank of electrical cabinets, we say, what would happen if this one blew up? And we calculate the zone of influence around that electrical cabinet. And we say, okay, if this cabinet dies, will we impact any of those important cables that we use to turn the power plant off? And so what they found is we've done tests historically with copper conductors. 3 phases are each in these bus bars. So it's not like a wire. It's a solid bar of copper. And there's 3 of them, 1 for each phase. And so we know, and we've calculated from past tests, what the zone of influence would be where we've destroyed everything in that circle. And one of the full-scale tests we did, we like to blow up old equipment, not new equipment. And so we had this old cabinet from Norway. And we blew it up, and it made a much, much bigger zone of influence than the copper ones. And we were like, what was in that? And it turns out that was aluminum conductors. And so then we surveyed the fleet of nuclear power plants in the U.S., and they're like, oh, yeah, we have that. And we're like, oh, no. So now we've got to find out, we've got to quantify this consequence, so when we do our risk analysis, we can say, this is how big of a circle to draw around that cabinet. So what we did was design some small-scale tests because we want to understand the physics of what's going on. So literally, we scaled down our bus bars to like 1 millimeter by 3 millimeters. So like teeny tiny, and we scaled the power down. And we did this at our lightning simulator facility at Sandia. So the guys there simulate lightning. And so now we're like, can we simulate a high energy arc fault? And they're like, sure. So what we wanted to do is do the small scale test so that we could build a model, an energy balance model, to be able to predict how big the zone of influence was and then validate that with the full scale test. So we needed to do this energy balance. We need to quantify the particle size, the distribution, and morphology. And we want to be able to quantify the degree of aluminum oxidation, because aluminum is just more energetic than copper. It gets excited. And when aluminum oxide is formed, it's really excited. And so there's some complex chemistry going on and plasma things going on, and we'll leave it at that level. Okay. So once we build the model, we'll be able to compare our predicted results from the experimental results at the full scale. So I'm going to attempt to show you what we have at Sandia, these really cool camera guys. The videographers, they have some cameras and equipment that are really cool. So this is zoomed in really fine, and this is between, I think it's a 5 millimeter gap between the 2 bus bars. So you can see the particles. It's slowed down really slow. You can see the shock wave that comes and the vapor that's there, and then the particles. And the video, the actual video can be run through computers that will track the particles and calculate the average velocity, the maximum velocity of all these particles. And you'll see that in a minute. So this is, again, the small scale test. He's pieced together for me some of the different views, but you've got, this is 1 million frames per second. Where's my camera guy? He's excited. So you can see it's in color. You can see the physics going on there, right? And then the particle imaging. I don't think he put the image traces on here. But he took 3 different camera angles, and we're going to send this. Actually, we're working with the University of Maryland. The professor there is going to be building the model, and we're giving him the data that we have. But we didn't wait to get the model for the full-scale test. I'll show you those in a minute. But what we did around the test, I didn't put a picture of the test setup, but around the test we're capturing some of those particles with carbon tape and aerogel. Aerogel is like 99% air. It's silicon dioxide, and it's really pure and clean, and so every little particles that get stuck in there, we know we can analyze. And so with the SEM, the microscope, and there's another that's on the next one. But these are close-ups of some of the particles at nanoscale, and you can see where they're spherical, so we can tell that it was molten. And then you can zoom in and see these dendritic growths, and so you know we can then send those through the analyzer and tell what's the makeup of those particles, right? How much is aluminum oxide? How much is copper? We used a copper shorting wire between the aluminum bus bars, so we know what material came off was from the shorting wire and what material came off from the aluminum, and then how much aluminum oxide was formed. So this will go all into the energy balance, and we can learn about the excess energy release above copper that aluminum is contributing to this event. So we did full-scale tests 2 weeks ago, so this is pretty new stuff. There's a facilities outside of Philadelphia called CANA, and they have 9 test cells, and their largest test cell, is this the laser? Is here. So they've got 3-phase power coming down the side. We park our electrical equipment. We had 4 identical electrical cabinets, just basic switch gear. We did all 4 of our tests at 6,900 volts. We did 2 different currents, 26,000 amps and 32,000 amps, and then we did 2 seconds and 4 second releases of the arcs. And so this CANA facility can generate all the energy, store it up in these big capacitors, these Marx capacitors, and then let it go in the 2 seconds or the 4 seconds. And we can't do this at Sandia without causing a brownout at Albuquerque. So this is a close-up of the inside, like if you take the door off of the electrical cabinet, and these are the 3 phases. These are the bus bars. They just look like bars, and they're coming out at you, and then they're turning down. And then there's an insulator, above it in the switchgear. So that's what we did was wrap a shorting wire, like 24, 32 gauge wire around all 3 of the phases, so that we knew we were causing a short, and we could make a good boom. And so now I have the color video. So this is about a 5-minute video, so I'm going to keep talking while it's going. So what we're looking at is a GoPro, because those are expendable. This is a GoPro up at the top corner of the largest test. So it was the 32,000 amps for 4 seconds. And it's slowed down pretty slow. What is in front of it there's 5 different instrumentation racks one on each side, and then you turn it back to full speed for you. 2 in front and 1 on the top, and we're measuring with radiometers. We're trying to capture the maximum temperature. We're trying to we also have carbon tape and aerogels in the instrumentation racks to capture some of the particles that are coming off. This is the other GoPro we have down on the other corner. And it takes, this is slowed down again, it takes about a half a second to breach the cabinet. And so you see the flames venting out of the sides of the seams of the cabinet enclosure, and then you can see it breach the cabinet wall. We have several other views that'll keep going, but you can see the zone of influence. You can see where there's a lot of high energy, high temp. We're trying to measure the pressure wave, the shock wave that's coming off, and you can see the hole that it created in the cabinet. I mean, it literally, in 4 seconds, vaporized 4 square feet of steel cabinet. We also put a camera, this is how you don't get hurt. We put a camera in the test cell, and it's right over here, and it's aimed at a mirror, a really high quality mirror. And so you'll see later on this camera's view right at the front of the cabinet. There's several views. We had a bank of cameras outside the test cell. And you can see what happens is the smoke pretty quickly obliterates your view, and you can't really tell what's going on. But you wouldn't want to be in that room. Nobody. So we didn't hurt our camera, but we're trying to see inside the smoke what exactly is happening. And so some of their cameras have a high dynamic range, and so you can see the difference in the video. We also had an IR camera, and what they can do is overlay the IR camera on top of the real picture, and then you can see through the smoke, and you can actually measure accurate temperatures off of it. This is the mirrored view, and you can see the front of the panel. See how it buckled? So that's the initial pressure wave of the arc. We did put some carbon tape and this other material that we could analyze later for the graphene structure to try to capture what the maximum temperature inside that. So here's the half second. You can see it vaporizing the front of that steel, and then you can see it breach. So that was all 1/2 second. And then it continues to cut that in half. So again, it gets obliterated. And you saw that it breached, and then there was like a step function in the energy. And so that's what we want to study, because that's when the aluminum gets involved, and you can see it. This is almost the one where he's superimposed the infrared on top of the, you can see the particles, because they were capturing them. What happened at the end of this test, there's an instrument, well, in the middle of this test, there's an instrumentation rack on the top, and all of its lines for the data acquisition system got severed. So they lost, on this test, they lost all their data from the top. So here we go. Here we've superimposed, so you can see this through the smoke. You can see it venting out of the sides of the cabinet. And then you'll see it breach the front. He slows it down for me. Sort of like a dragon. Yeah. And then you'll watch it. It's breached, and then it jumps. What we found in the small, and you can see the wires dangling. What we found in the small scale test was that the arc is made, and then the buoyancy of those hot gases causes it to rise up and break, and then the arc reforms. And you can see it pulsing, and we saw that only in the small scale. So when we're looking at the large scale, we're seeing that pulsing, and we're going to decide whether it was the phase, the normal sinusoidal pattern of the power, or if it was the arcing, reforming, breaking and reforming. It's pretty cool. Pretty cool stuff. Okay. Oh, now I can do things. Any questions on high energy arc faults before I change the subject? Talk about something even cooler, more important. Okay.
Where were you, Nick?
So we were in the control room, pretty far away. It's like one control room for all 9 test cells, so it's like in the middle. So we were like 2 or 3 test cells away. So we could see the chain link at the front, and we could see the splatter out of it, and we could hear it. But yeah, we weren't close. Nobody was. The cameras are all timed with the CHEMA control system, so they're all triggered at the same time. So everyone collecting data has the same 0. So.
Did you lose any cameras?
We lost both GoPros. On the one that was up high on in this test 3. Well, every day his lens got damaged, we had a separate cover on it. And so on the fourth day, we're like, well, he's pretty much toast. So they put him, I don't have that video showed, they put him on the floor, right? Like this is where it's going. They put him on the floor looking up. So the dragon like comes right out over the top of him. It's a pretty cool shot. Yeah. Yeah.
So, was the memory chips?
The memory chip was fine. Yeah. On this test, what we had was an extra battery pack strapped to the back of the GoPro, which was in a metal case, and that battery took some hits, and he was still functioning, but yeah, it's lithium, and so yeah, the memory chip was fine. We have all the data. Yeah,
Impressive.
yeah, yeah. Any more questions? Yeah.
Do you guys test with like fire systems that might come out in a situation like that, or do you go for like worst case scenario?
So we do look at both, but for a high energy arc fault, it happens instantaneously and it only lasts a couple seconds before relays and breakers upstream of the power shut it down. So that's why our tests are 2 and 4 seconds, because that's when the relays should kick. So no sprinkler is gonna touch that. Yeah, and have an impact on that consequence. Yeah, the ensuing fire, because now it's set everything in that zone of influence on fire, your sprinklers are going to come on if that space is sprinklered, and things are going to happen later. But we wanted to know how big is that boom. Yeah. Cool. Okay. So now we're going to talk about hydrogen a little bit. Something I also like. How many people saw the Hindenburg video? Everyone, right? Oh, the humanity. So hydrogen has a really bad reputational risk problem. People have a lot of bias against hydrogen. It's a pretty cool material, and it has a lot of ability to store energy. It has some unique capabilities that we can use it to, like, for other renewables, like the solar, right? You collect it during the day, and at night you're sitting with a candle. So there's different ways to store that energy during the day. Batteries is one way, but another way would be to use an electrolyzer and make hydrogen, stick it in a tank, and then run your fuel cell at night when you need the lights on. So there's a lot of research going into that, hydrogen as an energy carrier. I've done a lot of research right now on infrastructure risk, fire risk for hydrogen vehicles. So right now we have 5,000 light passenger duty vehicles on the road in California running on fuel cells, and about 32 retail refueling stations where you can go and refuel your car. And that was phase one. California is like leading the charge, right? And the next phase for hydrogen expansion is on the East Coast. And so the problem on the East Coast is the Baltimore Harbor Tunnel, the New York, New Jersey Port Authority, and MTA tunnels like the Lincoln Tunnel, the Holland Tunnel, the lower level of George Washington Bridge, and all the tunnels in Boston. They're like, no, we don't want your hydrogen vehicles in our tunnels, right? And so the problem is Americans won't buy a car if you get told you can't drive it to the airport in Boston. You're not going to buy that car. So they're holding back the expansion of the vehicles until they can solve the tunnel problem. And they have me working on it, so good luck. So we started talking with all 3 of those organizations in those cities, the tunnel owners. And we got the most warm welcome in Boston. The structural tunnel engineer at the Department of Transportation's like, yeah, I think renewable energies and less polluting vehicles are better, but like, to help me out, I'm worried about a couple of these things. We're like, okay, tell me your nightmares. So he's like, well, I want to know like what could happen, right? He's worried about specific things, what could happen, and when we described for him the level of rigor that the tanks on the vehicles have to survive, he's like, oh, okay, that's pretty good. Like, they take these tanks, they're really high pressure, they're 10,000 PSI tanks. The survivability test that these tanks have to survive to be allowed to be put in a vehicle, they're pressure cycle tested at extreme temperatures, extreme cycling frequencies. They're dropped on their end, on their side, on their 45, on the shoulder of the tank, which is the weakest part. They're then, after all these tests, they're put on a bonfire, like literally a pallet of and they're like, okay, you're on fire. And it has to not release the hydrogen until the bonfire's over the whole tank, and then there's a thermal protective device. It's a fusible link. When that tank gets so hot, it needs to release the hydrogen in a controlled way to prevent a catastrophic failure of the tank. And so these tanks really have to survive that. And so we explained a lot about that, and he's like, okay, so say there's a fire in the tunnel and it's venting it in a controlled way, but he's a structural engineer, so he's worried about spalling of his concrete. Both the floor, like normally they're pointed down, the vent is pointed down at the road surface. He's like, what if it's upside down and it's hitting my ceiling? And he's worried about explosive spalling from the concrete raining down on emergency responders. That's a perfectly good thing to be worried about. Let's find out, right? He's also worried about these concrete panels in some of the tunnels. I have some other schematics it's shown, but there's these precast concrete ceilings holding up the ceiling, and they're anchored into the rock, the bedrock, with these bolts. They're held up with this epoxy. So he's worried about the temperature of that epoxy being compromised, letting the bolts go and crashing the whole ceiling down on the people in the tunnel. Perfectly good thing to be worried about. Okay, so we did a comprehensive risk analysis. What could happen, right? And then if it does happen, what are the consequences? And then what are the chances of that happening? If we understood the consequence pretty well, we said, okay. If we didn't, if we were a little, like I didn't know. He's like, is my concrete going to spall? I'm like, I don't know. Let's find out, right? This is the type of event tree that we constructed for tunnel fires. It starts with an initiating event, an accident in a tunnel, and we assume that any accident happens to a hydrogen vehicle because that's what we want to look at. So every time we had to make a decision, we made a conservative decision. Like every car is a hydrogen vehicle, right? And we went through and we said, okay, is it a bad accident or just a minor accident? And we got tunnel data, real data from the US if we could find it, worldwide if we couldn't. So we have data from Norway, we have data from whatever's published. And we could do sensitivity analysis around these probabilities because it's easy to build a Monte Carlo on this event tree. And what we use to determine minor or severe is if an accident had injuries or fatalities. So if nobody's hurt, it's probably a fender bender, and you probably haven't hurt the hydrogen system either, right? We also have data from the from NHTSA doing crash testing. There's not a lot of tests. They've only done 5 or 6 full-scale tests with fully loaded hydrogen vehicle with the same side impact, rear impact, corner impact tests. So we have that data. None of their tests released any hydrogen. So that's reflected in this too. And so what we've done is create these event trees, say, what if this happens? It's a severe, there's a fire, no hydrogen's released, but then the fire spreads and we get the TPRD releasing the fire, right, and the hydrogen catching. And so we calculated all this, and these colors at the end correspond to, like, did hydrogen contribute to the consequence of the accident? If all the hydrogen stays in the tank or in the fuel system, then no, it's green, right? I mean, it still could be property damage, but you've not contributed to the consequence with your hydrogen. So the red ones are the cool ones. These are the catastrophic tank ruptures that some people say would never happen, but I'm never ever going to say nothing's ever going to happen, right? You can't be a risk analyst and say it's never going to happen. Just run away from that person if they say it. So we've got some red scenarios, and then some yellow ones where hydrogen does contribute to it, but let's understand that. So when we calculated the probabilities and we looked at like a pie chart of what's the frequency of those probabilities, you can see that the red, those bad ones are just tiny. The probability is really tiny, and people are doing, in the hydrogen industry, safety industry, they're doing a lot of consequence testing on these tiny little probabilities. Yes, we need to understand the worst case, but for a tunnel owner, he has to make a regulation. Is he making a regulation on the worst case? No, you all got in a car today. You all did, right? Or some sort of vehicle, unless you rode your bike. Anyway, we've all ridden in a car, right? So we can't base our risk decisions on the worst case. It has to be analyzed. And so we looked at this branch line G it's yellow. It's the biggest probability of the hydrogen having a contribution to the consequence. So this is that TPRD venting into an existing fire. So it's a hydrogen vehicle and a gasoline vehicle crashing together. The hydrogen vehicle ends up upside down. There's a fire because gasoline tanks just break. And eventually it gets hot enough and the hydrogen in the tank vents. And we made worst case decisions always. The hydrogen tank was completely full. It was one tank instead of 3 tanks, like the Toyota vehicle, right? So we're releasing all 6 kilograms instead of just 1 tank's worth, right? It takes about 5 minutes to blow down a tank through the TPRD. And so we assumed that the maximum mass flow rate was coming for the entire 5 minutes. Like, we really made this very conservative worst case estimate. And so you can see we calculated what the temperature might be at the ceiling, just using numerical calculations. And so we peeked over. This purple line is the current regulations about what a tunnel has to survive. Temperature-wise, it's based on a tanker truck burning for 2 hours in your tunnel. And so we're like, oh, it went over. And that hydrogen kind of burns hot, but only for a few seconds, right? So, but this blowing through the current regulation made him worry. So we're like, okay, I understand your worry. But the heat release rate, if you look at it, here's that tanker truck burning. The blue line is a bus. And so a light passenger vehicle just venting his hydrogen into an existing fire, which is already a problem, doesn't violate the heat release rate regulation, but the temperature, it went over. So he said, analyze this for me. Find out, is my steel going to be compromised? Find out if my concrete's going to be compromised. And so this is the schematic I was talking about, where the bolts are anchored up into the bedrock. And if we put a fire conservatively right on that steel support, so that we could have the best chance of getting the heat up these hangers and into the bolt. We looked at 2 different typical tunnels in the Boston area, and we looked at the potential for spalling the concrete. So we did this with and without ventilation. So tunnels have ventilation. Some older tunnels have crappy ventilation, and sometimes the ventilation kicks up to a higher level during an emergency, and sometimes it doesn't work. So we're like, okay, conservative. What if the ventilation's not working at all? And so we looked at this hot spot on the ceiling. And you can see it's about a 12-foot diameter hot spot, and it gets pretty hot. It gets close to 2,000 degrees. It's not going to last 5 minutes, but it could, right, if it vented for 5 whole minutes, if the flame stays touching the ceiling. The thing about hydrogen, there's no C's, there's no carbons, so it doesn't radiate. It radiates very weakly. So you could hold your hand this far away from a hydrogen flame and not move it. It's not hot next to it, it's hot in it. And it's very hot in it. So as long as the flame is touching the ceiling, you get this hot spot. And so we have CFD models and heat transfer models of the concrete panels and the actual tunnel itself. And then we turned the ventilation on. You can see that was a 12-foot diameter hot spot. And with the ventilation on, it blows the flame over like you would expect. And so we could use these models were developed for nuclear weapons, so they're really, really precise. So I trust these models. These aren't models that you can use. They're internal to Sandia only, but this one's called Fuego. It's fire. And so we can take the boundary conditions at the top of the tunnel and import it into the heat transfer model, which calculates the heat transfer through that block of concrete. And so you can see with the ventilation on, you get this vortex that's pretty well documented in fluid flow. And you can see it's more like a 7-foot diameter. So ventilation really helps lower that hot spot. It also lowers it out of the 2,000 degrees and takes under 1,200 degrees. So it takes a lot of the heat out of that hot spot. So then we looked at the maximum temperatures and we compared that to some other research that had been done on concrete spalling. And we found it takes about 30 minutes of exposure to a hot fire to drop concrete, to make the explosive spalling happen. There's several mechanisms in that happen. It's actually kind of complicated as well. But we're nowhere near. If it were a straight up blowdown, the flame would be impinging on the ceiling for about 1.5 minutes, not 30 minutes, right? So we were able to tell the structural engineer that that's really unlikely that you're going to spall from the hydrogen. If you've wrecked several cars and you have a big hydrocarbon fire, you could probably spall. It happens now. You can find pictures of tunnel spalling. On your steel, you're going to be, here's the epoxy melts at 140 degrees, and it starts to degrade around 90 degrees. Well, what we found is up at the top of that, the shortest hanger, the epoxy is still at ambient temperature. So we can tell them, your concrete bolts are not going to come out of your tunnel. Concrete's not going to fall on people. And so he said, yeah, this is great. I'm going to buy a hydrogen vehicle, right? These are safer than gasoline because the hydrogen stays in the tank. But our problem right now is that he was not the lead engineer for Massachusetts Department of Transportation, and he recommended to the lead engineer that they allow the vehicles, and she said no. She didn't want to accept any additional risk because she didn't even read our report yet. So we're working on that. It's a reputational risk, and nobody wants to be first. Nobody wants to be the first one to allow these vehicles in their tunnel. So now what we're doing is working on a national solution. Instead of tunnel by tunnel, I'm working with the Federal Highway Administration and NHTSA, and we're going to try to get all the tunnel owners together in like a stakeholder group to say, give me your nightmares. I'm going to show you what the real analysis shows and what you can decide. And maybe we can say, okay, tunnels that have good ventilation, tunnels that have sprinklers, tunnels that have an emergency egress tunnel, because they're worried about public safety. Those tunnels are fine. And so it may be that the Holland Tunnel and the Lincoln Tunnel that were built in 1927 don't ever allow them. But that's okay because you could take a bridge, right? But in Boston particularly, their tunnels are in pretty good shape and they're kind of new, especially once you go to the airport. So I think I'm optimistic. But what's really cool at Sandia is I'm working on a problem that matters to the country. That's pretty cool. So that's it. How did you do on time? Oh, I went over.